Okay, now let's look at one that does work. And that's the one where we're only left with this term right here. Okay? Okay, so what if we pick that to be our loop invariant? Okay, and what if we now say, again, it's not that hard to reason through what the loop guard must be. It's not that hard to reason through what the initialization step should be. The loop guard is A top left is not all of A. The initialization step is pick A top left to be 0 by 0, because then you end up with a 0 by 0 matrix times a vector with 0 elements in it that disappears, and then you find that Y top is empty and Y bottom is all of Y hat. And that's the state in which you start because of the precondition. So that's good. Okay, so now imagine getting into the loop. And now what you would like to do is say, I repartition my matrix, exposing a row and a column. What is the state in terms of those exposed pieces? And notice that if you expose a row and a column of A, then you must expose an element of X, the top element of X bottom, and the top element of Y bottom. Okay, how do we go about this? Well, we say this is what must be in Y at the top of the loop. That's the loop invariant. We now repartition exposing pieces. We then do textual substitution of those pieces into the loop invariant to find out what the state must be before the actual update happens in the loop body. So what do we do? Well, let's just repeat this. I like just that's our loop invariant. And we now say at the top of the loop we repartition. Y top becomes Y0. A top left becomes A0, 0. X top becomes X0. Y tops becomes X0. And similarly, we get that Y bottom becomes Psi1, Y2. Let's actually write it like that. And that has to be equal to, and then this becomes Psi1 hat, Y2 hat. Okay? That's the state of the vector in terms of the exposed pieces, and we get that by doing the textual substitution. All right? Now, what is it that we do at the bottom of the loop? At the bottom of the loop, we say, take these pieces that we've exposed and create the quadrants and the partition vectors from them, like that. And notice that where we are in the matrix now has moved forward by one row and one column, and similarly we've gone one extra element into vector X and one extra element into vector Y. Okay, so the state at the bottom of the loop, we can similarly start by saying we know that we have Y top, Y bottom is equal to A top left, X top plus Y top hat and Y bottom hat. Now, however, A top left has become this submatrix right here. So we do a textual substitution. Okay? And then we need to multiply that times x0 I1. We need to substitute in y0 hat psi1 hat. This becomes y2 hat. This becomes y0 psi 1, and this becomes y2. Now there's one catch. Remember, A is a symmetric matrix. And since A is a symmetric matrix, this right here is not actually stored. But we know that this here is part of a row of A, and therefore this column right here is just that row transposed. So in our expression, we really need to put in A10 transpose transpose. Let's actually put it in that way. Okay, because the A10 transpose really is a label that we give to this part of the matrix, and we need to take what's in that part of the matrix and transpose. You got it? Okay, now all we have to do is apply the rules of linear algebra. This is actually equal to, and now we can multiply it out. This times that plus this times that. Okay? This times that plus this times that plus that. Okay? And y2 hat. Okay, it's just a matter of working out what must be in the vector. What does the linear algebra tell us must be in the vector? So what we just did is derive step 7 for the worksheet, the state of the variables after the update, and if we then plug that into the worksheet, this is what you get. Okay, so this is what's true at the top of the loop in terms of these pieces that we expose. This is what's in the vector at the bottom of the loop in terms of the pieces that are exposed. We need to somehow figure out how to update from here to here. Okay, how do we do that? Well, we can read it off. We know that y0 must be equal to chi00 x0 plus a10 transpose transpose. Actually, this is a vector. Remember, it's a row vector transpose becomes a column vector times a scalar. We can bring the scalar up front. So let's actually do that. Plus y0 hat. Okay? Psi 1 must be equal to A10 transpose x0 plus alpha 1 1 times chi 1 plus psi 1 hat. y2 must be equal to y2 hat. Now, we don't want to go and compute all of this, because then we would be computing again with a part of the matrix with which we already had computed before. What we do instead is we say, oh, y0 already contains this times that. That's this part right here. Okay? So all you need to do is update y0 by adding chi 1 times a10 transpose transpose to it. Oh, that's a scalar times a vector added to a vector. That's an Axby operation. Okay? Then you look at psi 1 and you say, well, psi 1 already contains its original contents psi 1 hat. So this is already in psi 1. And what we need to do is update it with this dot product plus the scalar product. And that tells us how to update psi 1. And then we look at y2 and we say y2 already has y2 hat in it. It needs to have y2 hat in it, so nothing needs to happen to it whatsoever. Okay, and then we conclude that the actual updates are that y0 is updated with psi1 times a1 transpose. That's the row vector sitting right here, plus what's already in y0. And psi1 has to be updated with the dot product of a1 transpose, this row vector, with x0, to which we add the product of alpha 1 times chi1, and we must add that to what's already in psi1, and this then becomes the actual computation in the body of the loop.
Okay, so what we just did was compare the result of step 6 with step 7, and that then yielded the actual update step, which we can then plug into the worksheet, and this is what you get. And then in the end, we just take away all of the annotations out of the worksheet, and we're left with the actual algorithm that has been derived to be correct, ready to be translated into MATLAB code.
Okay, and notice, it's systematic. Trust the force. You just push through the linear algebra and everything falls in place.